Welcome to ECE 302. This is Lecture A.7 on Review of Linear Time Invariant Systems. I'm Professor Stanley Chan. So today we're going to learn about the linear time invariant system, something that I believe many of you have already learned in another course called the Signal and Systems. So why are we studying this topic in probability and random processes? Well, this is because when we talk about random processes, we want to know how the random process behaves as it goes through some kind of operation. And the basic operation that we're going to look at is what we call the time and linear and time invariant system. So to start with, I want to give you a preview of the problem. Suppose we have a random process, I call it x of t, and then I send it through a system. Now, for those of you who are not electrical engineers, this system, you can just treat it as a black box. Okay, so you send this random process x of t through a black box, and then you're going to get some output we call it y. Now, this kind of relationship is extremely common, even though if you're not doing signal processing or communication. Even if you think about a data science problem, you will have problems like these. You have some kind of output, you do some operations on those outputs. For example, a running average of all these samples over the time, you get a weighted average of your signal. This is already a system. The averaging operation that you put onto the data is what we call the system. Okay, so it is very common to study this problem in any practical scenario, because this random process really have limited usefulness until we apply operations to them. And then for y-sense stationary processes, there is a very beautiful system called the linear time invariant system. And this system allows us to do many useful operations, including the notion of convolution, correlation, Fourier transforms, and so on. So in signal processing communication, of course, this is extremely popular because you have some statistics of the signal, and as you transmit the signal through certain kind of systems, you want to know what is the output. The inverse problem is also very, very popular, whereas in speech processing, for example, you receive some kind of signal which is corrupted by the communication channel, and you want to recover the signal, and you know some statistics of this random process, and so you want to study this problem in the lens of this linear time invariant systems. So I want to give everyone a good overview of this linear time invariant system, and so I want to share with you a running average example. So imagine that you have a discrete time signal, and then this discrete time signal you have these samples. This is what we call the x of t, or in the discrete time domain we call it x of n. They are just denoting the same thing. Here, this square bracket of n denotes is a discrete time signal where you have index is 1 over 1 through n. So this is the input. This is your x. Okay, so this is input. Now, in many cases, you are not just interested in looking at the statistics of this input, because let's say this is the stock market values recorded over the minutes or over the hours. This is the input data, and you're not interested in looking at this input data and do all the calculations. What you really want to do is to predict what will happen in the future. So what do I mean? Well, you look at this pattern, and then you want to ask what will happen in the next time stamp. That is a legitimate question to ask. So how do you do this problem? Well, the way to do this problem is to look at some statistics, and I'm just showing you one of the simplest possible way of looking at the statistics. So let me just define a signal called Yn, and this Yn is defined as xn, okay, plus x of n minus 1. Just extremely simple combination of the current value and also the previous value. Now, of course, we can also make it a little bit more interesting. How about we say that it depends on n minus 1 and n minus 2. I want to make a prediction, okay? And I say that it is going to be A and then B of these two samples. All right. Okay. So what is it? Well, so you say that your yn, which is a sample over here in the output, is going to be a linear combination of the n minus 1 sample and also the n minus 2 sample. So essentially, you're doing this A weighted average, right? So let's say I am looking at these two samples, right? So this is n minus 1, this is n minus 2. I want to predict the future at this timestamp, right? So at this timestamp, of course, these two I am not able to predict, but at this timestamp, I'll be able to take a weighted average between this one and that one, and I will say that here is your yn. Okay. Now you can extrapolate this idea. Basically, when it goes to here, it will become the weighted average of this sample and that sample. So you have something right here. So you will be able to get some signals like these through this relationship. And this is exactly what we call the system, where the system is specified by this coefficient and this coefficient. And so you can think it as you have a system, okay, and the system is given by this A and this B. You send a x of n through the system, you are going to get some yn. Okay, and of course you're sending a sequence of xn's, and then you're getting another sequence ofyn's. And this is a system. Now there are many systems, and the system that we are interested in studying is called the linear time invariant system. It's a system that allows you to model problems like these, where as you changes the time index of your input, correspondingly you will also change the index of the output. And so that is very useful when you think about running average as an example. So what is the meaning of LTI, right? LTI stands for two things. Linear, that stands for the L, and time invariant, that stands for the TI. Okay, so altogether it's called a LTI system. So for the linear time invariant system, let's look at the first part. It is the linearity. So let's say if you have two input functions, x1t and x2t, they're both random processes. You send them through a black box. Okay, so x1 of t, you send it through a black box, you get y1 of t, and then you send x2 of t through the same black box, you get y2 of t. So you get these two. Now you define another signal, you call it z of t. Okay, so let's call it x of t. Okay, so x of t, which is a of x1 of t plus b of x2 of t. As you send this overall signal x of t through this system, what you're going to get is y of t that is going to be a linear combination of y1t and y2t. And if it is linear, then you will have a and b. Okay, so in other words, this a, this b will be preserved after as it goes through the system. In addition, this operation sum will be preserved. So you will not get x1, x2 as you go through the system. You won't get x1 square or x1 cube plus the cosine of x2. It has to remain as a times x1 and b times x2. As you go through, you will have a times y1 and b times y2. This is what we call the linearity. The other property that is also important in a linear time invariant system is, of course, the time invariance. What this says is that you have this block, and then you send this x of t, go through this block, you get y of t. Now, as you change the time index to another one, to a t plus some offset, time offset tau, you're going to get the output as y t plus tau. Okay, so whatever amount of shift you have for your time, in the input, you will get the same amount of shift in the output. So this is called a time invariant. Now, by looking at this linear time invariant system, you realize that it is really the system that we want to know, because if you think about this running average problem, the linearity is essential to allow you to deal with this operation A and B, because you're multiplying the signal with two constants. The shift invariance is significant because as you are moving along this time axis by changing these two indexes, the corresponding output has to change. Just like here, you're looking at this, the third timestamp, then you're looking at these two, right? Now, if you're looking at this timestamp, of course, then you're looking at these two. So this shift invariant, time invariant property will allow you to do this moving window, that kind of operation, which is significant in most of the time series. All right, so after we have introduced the idea of linear time invariant systems, I also need to remind everyone about a very basic operation called the convolution. Convolution, it is a basic operation for LTI systems. Now, of course, many of you have already learned convolution, so this is really a review. The convolution between a function x of t and then another function h of t is denoted by this star operation. And this star operation is defined as the integration of h and x, where the integration argument is tau, and then this t has to be matched with respect to your output. So this t is to match with this t, and then the tau is integrated over the inside the integration. We have a name for this x of t. This is called the input. We have a name for this h. H is called the impulse response. The h is called the impulse response because if you send an input, okay, as an impulse, so if x of t is the delta function, as you go through this convolution, what you will see is that you will just do the integration, you keep the h of tau, but then now this x of t minus tau will become delta of t minus tau. So what you're doing is that you're doing this integration of h tau and then delta t minus tau. And we know that this delta function has a property that it will just shift this h of tau towards this time index t, and therefore the output will give you h of t. What it means is that if you send the delta function as the input, you go through a system which is characterized by some function h of t, then the output will just be the shift version of your h of t. So let's say there's a 0, there's 0, there's a 0 here. As you send it through the system, you will get a pulse like this. Okay, so this is the convolution, and so this is called the impulse response because you send the impulse in, you get the response to this impulse. So convolution is basic operation because convolution is defined for linear time invariant systems. If your system is not linear time invariant, this convolution doesn't work. A very important property of the convolution is that the convolution is commutative. What it means is that convolving h with x is the same as convolving x with h. The order of the convolution does not matter. Putting into the equation, we have this integration of h with x of t minus tau. That would be the same as integrating h of t minus tau and x of tau. These two are the same. Now, after we have looked at the convolution and the basics of LTI systems, I also want to give a quick review of the Fourier transforms. For any linear time invariant systems, the output yt can be determined through the Fourier transform. The Fourier transform of a square integrable function x of t is really defined by this integration. Inside this integration, you have the function x of t, and then there is an exponential function e to the power minus j omega t, and you integrate this function with respect to the time, then you can get a transformed function, which is now a function in terms of the omega. This is called the Fourier transform, and I believe many of you have already seen this in the Signal and Systems course. Now, of course, in this course, we are not asking you to derive the Fourier transforms from scratch. Most of the Fourier transform pairs will be given in the text and also in exams and also for the homeworks. If you go to the course website, you will see a table containing all the necessary Fourier transforms for our course. As you learn Fourier transform, I'm not sure how many of you are paying attention to the following three important things about the Fourier transforms. So I decided to go through them with you. Now, there are of course many other properties of the Fourier transforms which are extremely useful. I want to highlight these three because these three are very fundamental to do any signal processing. The first property is that the Fourier transform is an orthogonal mapping. This is a very important thing to know because you're not just doing an arbitrary mapping from one space to another space. You're doing an orthogonal transform from one to the other. As a result, many of the nice properties, in particular the distance properties, are preserved. The second property that is important to know is that why do we care about this ej omega t so much? It is because that the ej omega t is an Eigen function. It doesn't change as it goes through a linear time invariant system. That is unique to LTI systems. The third thing that many of you should have remembered so far is that convolution in time is equal to the multiplication in what we call the frequency domain. That will allow you to do a lot of operations of the random processes very efficiently in the other domain. All right, so let's first talk about this orthogonal mapping. What is Fourier transform? Well, Fourier transform, of course, is operation, right? It is this operation. It's going from one space to another space. The original space that you're living in is a perpendicular space where you have two axes. You have x1, you have x2, and then there is a right angle between the two. Okay, so this is the coordinate system that we all live in. Now, if you like to have a three-dimensional space, you have x1, x2, and x3. Everything is orthogonal. And if you apply the Fourier transform, I'm not sure if you are familiar with this idea, that if you apply the Fourier transform, you are not going to destroy this orthogonality structure. What you will have is that you will have this property. Okay, certainly this is omega 1, omega 2, and omega 3, right? What is so important is that any point, any pairs of points in the original space is preserved in the new space. That is an extremely important property of the Fourier transforms. So anything that you have in the time domain is guaranteed to show up in the Fourier domain, and that's a one-to-one mapping, as long as your function is well defined. This property is essential so that you can define this inverse mapping, call it the inverse Fourier transform. So you can go back and forth. Okay, and so that's why this Fourier transform is orthogonal mapping. If you are familiar with the matrix operation, this Fourier transform, this F, can be written as a matrix F, and then all these functions you can call it X. So you're applying a matrix F to a vector x, and that will give you a vector y. Okay, so this is the Fourier transform written in the matrix form. You have the signal, you have the Fourier transform matrix, and then you have the output. The nice thing about the Fourier transform is that if you apply the Fourier transform matrix, you apply the Hermitian, which is the complex conjugate, and the transpose, you apply to this, you will get back x. Okay, so what it means is that, in other words, this thing is equals to identity, meaning that you do not really need to define this Fourier transform inverse. It's just the Hermitian transpose of the original Fourier transform matrix. You will get back the identity matrix. So this is a very, very nice property that makes the operation extremely easy. All right, and so this orthogonal mapping is something that we are not going to use it for this course, but for many other courses that you will learn in the 4th year or in the graduate school, this property will come back very often. So just to remember, the Fourier transform is orthogonal mapping. The second important message that I want to share is that this function ej omega t, this very funny function, why do we care about this function? It is because that this function is an eigenfunction. An eigenfunction means that if you have you have some function, okay, in general, an eigenfunction is that you have some function x of t, you go through the black box, you will get x of t back with some scaling constant a. So whatever you send in to the system, you will get back. It turns out that if x of t equals to ej omega t, you will indeed get back something like this form. And as such, your ej omega t is an eigenfunction. So why is this true? Well, if it is a linear time invariant system, you can write down the impulse response convolve with your input as this convolution between h tau and x of t minus tau. Then you can plug in your t minus tau, the x, with this proposed function ej omega t minus tau. And then if you go to here, you realize that this ej omega t has nothing to do with your tau, and so it can be pulled out from the integration. And therefore you have what? You have this integration of h of tau d tau times this ej omega t, and this is precisely the Fourier transform of your h. And therefore you can show that your y of t is equal to something that doesn't change over time times the original function x of t. And therefore your x of t being e to the power j omega t is indeed an eigenfunction. So why do we care about eigenfunction? Well, because if you remember, any function x of t, according to the Fourier series, you can write it as a n e minus j omega n t for n going from minus infinity to infinity. Any function, as long as they are square integrable, you can write this function into this infinite series. And if you can write it in this infinite series, and we know that each individual component is eigenfunction, that means as this function goes through the linear time invariant system, all these exponential functions will be preserved. What will be changed is just that your coefficient will be amplified or diminished according to some scaling constants defined by the system. The system will give you some kind of operation. That leads to the third property, which is that the convolution in time will give you the multiplication in the Fourier domain. In other words, if you send this function x of t going through a linear time invariant system with this h of t, you get the output. You know that y of t equals to h of t convolve with x of t. You will in the Fourier domain, you will get y of omega equals to h of omega times x of omega. This is an extremely important property, okay? Because many times doing this convolution is a nightmare. However, doing this multiplication is a very easy thing. So now you can connect the dots. What do we have? Well, the second property says that if you send in any infinite series in this Fourier series form, you will be just doing this amplification or attenuation of this constant, which is to do some operation on to this coefficient an. This part is preserved in the Fourier domain. So when you do this amplification or attenuation of this an, this is exactly doing this. You have your signal, and then you have your system response, which is multiply them together. You are not doing anything towards this exponential component because this is an Eigen function. And afterwards, what do we have? Afterwards, after you do this multiplication in the Fourier domain, you can use the first property. The first property says that now you're in the Fourier space. Just do the inverse mapping. Since you're doing the orthogonal mapping, the inversion is well defined, and so you can go back to say that if I do all the operations in the Fourier domain, I can just go back to do the to obtain the results in the time domain. And so all these three components, as you can see, that all these three components, they tell one story. That how do you go from one space, the time space, to the Fourier space and go backward, right? And why do we have this convolution in time equals to the multiplication in the Fourier domain? And these are playing a very important role in random processes as well. It's not just limited to deterministic functions. They are also very applicable to random processes. So what we are going to do in the next lecture is to look at this problem. What happens as we send the random process through an LTI system? Obviously, we will see convolution, but what will happen to the mean function? What will happen to the autocorrelation function? What will happen to the cross-correlation function? And what will happen to the power spectral densities? These will be analyzed in the following lectures. So to end this lecture, I will just point everyone to a very classical textbook on signal systems by Oppenheim and Wilsky. Many of these materials should have been covered in a companion course at Purdue. So you're welcome to take a look at those. I want to emphasize that the concepts that we are discussing here is not just limited to electrical engineering or computer engineering. Even for computer science, we need to know this thing. For statistics students, this would be equally applicable. As I said, that you have this running average, that kind of operations. Those can also be modeled through this linear time invariant system. It's just that the terminology may not be that familiar with you. The techniques are equally applicable. All right, so in the rest of this chapter, what we are going to study will be the following. We assume that x of t is an input, yt will be the output, and then we want to look at this LTI system related by this convolution operation. So this is the end of today's lecture. I hope you have learned something. If you have any question, please let me know. I will be very happy to help you. Thank you very much.